This is absolute mathematical proof that a loop is impossible in the 3x plus 1 problem, the Collatz conjecture, which holds for every possible sequence within infinity. And in this proof, I term every 3x plus 1 y. In order to have a loop, every value of x in the loop must have all the rises and descents between it leaving and coming back to itself must cancel out with each other to leave a value of 0. In other words, they must have a net rise of 0. I prove this impossible in 5 steps of deduction. Step 1. Between the first x and the first y minus 1, we have 2x, which we can cancel out with the final y to the final x. This leaves a value of y minus 3x between the final y to the final, also the first x. Y is always even, x is always odd, 3x is always odd, so an odd number from an even number leaves an odd number, so y minus 3x is always odd. Step 2. So we now know we must get an odd number as a net rise for all values between all y's to x's and all x's to y minus 1's between the first y and final y minus 1 to cancel out with the final y minus 3x and leave 0. Step 3a. In the case where the value of x is higher than the previous x, there is always 1x between y to x and 2x from that x to the next y minus 1. So we can cancel out the 1x between y and x with the 1x between x and the next y minus 1. This leaves a value of 0 in the descent between y and x and a value of 1x in the rise from x to the next y minus 1. This always gives us a net rise of an x, an odd number between y and the next y minus 1, where the value of x is greater than the previous x. Or 3b, in the case where the value of x is lower than the previous x, there is always an odd number of x's in the descent between y to x and 2x from that x to the next y minus 1. So we can cancel out the 2x in the rise between x and y minus 1 with the lowest 2 x's in the descent between y and x. This leaves a value of 0 in the rise between x and y minus 1 and a value of y minus 3x in the descent from y to x. This always gives us a net descent of y minus 3x, which is always an odd number, between y and the next y minus 1, where the value of x is lower than the previous x. Step 4. This means we need either a, an odd number of net descents subtracted from an even number of net rises to leave a net rise of an odd number, or b, an even number of net descents subtracted from an odd number of net rises to leave a net rise of an odd number. Because we must have either a or b to satisfy condition 2, it means we must have an odd number of x's between the first and final x. However, here arises an unavoidable inequality. For a loop to happen, every value of x must have a net rise of 0 in order to return to itself. So calculating from the lowest odd value of x in the loop as a starting x, which we'll call xn, we know the next odd value of x, xn plus 1, must be higher. So the difference between 3xn plus 1 and the final y before xn, which we'll call fy, must also be an odd number. But now we have an even number of x's between xn plus 1 and fy. So we can't get an odd number to cancel with the fy minus 3xn plus 1 to leave a net rise of 0, because an odd number minus an odd number leaves an even number, and an even number minus an even number leaves an even number, and an even number cannot cancel with the final y minus xn plus 1 multiplied by 3, which is an odd number. Just to clarify, fy can't be 2xn, because then xn minus 1 would be lower in value than xn, which is set as the lowest x. So there are two options to consider. Either fy would be 8xn or more, or if xy were 4xn, then xn minus 2 couldn't be lower in value than xn, because we are measuring from xn as the lowest value of x in the loop. So 3xn plus 1 must be lower than fy, or the y before xn minus 2. Both of these y's are even, so minus 3xn plus 1 would leave an odd number in both cases. However, both would have an even number of x's between xn plus 1 and either of those two y's, still giving an inequality, making a loop impossible either way. So it's impossible to get a second loop in the Collatz conjecture regardless of any starting value of any x in any sequence within infinity. Proven on the 16th of May 2024 by me, Sean Anthony Gilligan, independent mathematician and physicist.